Welcome everyone. It's 2 o'clock now in Taiwan. I think it must be what 10 o'clock. Oh,
It's
in
8 o'clock.
in Italy, right? You're in Italy. Italy. Where in Italy?
Germany, Germany.
In Germany. Very good.
Yeah.
Okay. And today's speaker, we are very happy to be able to invite Dr. Elias Roussos to give a talk in this series. And Elias, let me just say a few words to introduce Elias. He studied at the at the University of Athens, got his bachelor degree there, and then he went on to France, getting his master degree in space studies at the International Space University in Strasbourg, and then he went to Germany to get his PhD as a PhD student at the Planck Institute for Solar System Research in the early 2005 and 2008. And since then, he stayed on and working very hard. Yeah, I can tell you that he works very hard at the institute. And he now is actually I would say the leading expert in the energetic charged particle in the metrosphere of Jupiter and Saturn, and presumably other outer planets too. And he's now a senior scientist at the Max Planck Institute for Solar System Research. And his research interests include planetary space weather, the moon and ring interaction with the solar wind, and the planetary metrospheres. And those are very interesting topics too. And then about the radiation belts of Jupiter and Saturn. But today he will be talking about, because our series, the mini moon series, is about the moon. So I think he take up some of his interesting work on the moon, and to talk about the energetic charged particle interaction with the moon. Okay, Elias, please go ahead. Thank you.
Okay, so let me start. Good afternoon for you, to everyone, and thanks, Wink, for this nice introduction. So what I was asked to, or what I plan to present to you today, is the science that we can do at the moon through high energy particles. This is a bit of a strange topic, I would say. So if you start looking about energetic particles at the Earth's moon, in ADS, for instance, in a literature database, you will find out that almost 90 or even more, 95% of the papers about this topic concern really space weather, like the total ionizing doses on the surface and the safety of the astronauts, and how we can protect the astronauts and the devices we send to the moon from using the lunar soil, and so on and so on. And there is very little part which really deals with actual science using energetic particles. So my task here is to not talk about space weather as much as possible, and try to give you a summary of all the opportunities we have to do science on the moon by using high energy particles. And the other aspect of this talk is that because, at the moon we have the chance to send bigger experiments, more experiments. We can do very high precision measurements. This can be kind of a test bed for all the type of experiments that we might want to do and prepare for when we go to the outer planet moons. Because the outer planet moons, they are continuously exposed to energetic particles, unlike our moon. However, the moon is a very good opportunity for us to test theories to their limit with high precision, and also prepare to do the same type of science and even more at the outer planet moons. Okay, so let me start with this presentation, and I think it's very useful to begin with a kind of a definition for energetic particles. So if you look in the literature, you will not really find any consistent definition. I think maybe everyone has his or her own favorite definition of what energetic particles is. So the definition really changes, especially if we talk about what is the lower energy limit, from where do we start to measure energetic particles. There is no single answer to this, so it really matters about which environment we are talking about, the context, the kind of study that we are doing. It matters about what type of material we interact with, what is the strength and the type of material that we have the interaction with. Sometimes we even separate, energetic and low energy particles based on the instrument type. You know that going from plasma instruments to energetic particle instruments, there is a switch somewhere around 10 kV. So traditionally, the higher energy part, it's simply, let's say, it's the instrument which measures energetic particles. You can see here some spectra. You see that the proton spectra here in the solar wind, if you can see also my cursor, it's a very broad spectrum, starting from a few kV and below up to going up to giga electron volts in the cosmic rays. That's a typical electron spectrum in the solar wind with which, the moon is interacting. And in the solar wind, usually the solar energetic electrons, they don't extend much more than a few hundreds of kV. But for this presentation, and I will explain why, I will focus mostly on energies above 10 kV up to several tens of giga electron volts. And the reason I'm doing this is because for the lower energy limit to start with, this kind of energies, this kind of energetic particles, they have the chance to directly interact with the surface. So even if the surface of the moon is charged, and I will explain what surface charging means in the later slides. So if you have a potential of the surface, usually they do not exceed this 10 kilo electron volt limit, which means that a particle like an electron, even if you have a 10 kV, 10 kilovolt negative potential on the surface, it's able to penetrate it and really interact with the surface. So the other reason that I choose this limit is that because above this energy range, we have typically no neutralization and not much of backscattering. So what dominates when these particles interact with a lunar surface is mostly implantation into the lunar soil. Plus, also we have reduced or no impact from lunar magnetic anomalies. I will also talk about lunar magnetic anomalies in the next slides. So you can see here about 10 kV protons, how much they will penetrate, several hundred nanometers into the surface. This is another measurement here. That's a measurement of energetic neutral atoms coming out of the moon. So energetic neutral atoms are primary protons, let's say, coming from the solar wind. They get neutralized, backscattered, and we can see them. We can measure them with kind of a particle camera, let's put it this way. And you can see that the spectrum above 1 kV drops very, very sharply. So I think up to above 10 kV, we're well into the energetic range. And what about reflection of particles, charged particles like you see here? That's the primary solar wind protons, primary alpha particles from the solar wind, and this is the reflected part from the lunar surface here. And you see that the reflected part goes up to about 1 to 3 kV, and beyond that, mostly we have implantation. So that's one way to define energetic particles and define the lower limit at 10 kV. Okay, so then having that, okay, let's talk about the different regimes that we have of energetic particles in the heliosphere, in the solar wind. So I defined 3 different broad ranges. You can see them here. You see that these circles here, they intersect. What I want to mean by this is that we should not really put any hard boundary here. I give indicative boundaries. So let's say the first one, which I call the suprathermal or soft energetic particles, are approximately between 10 kV and up to 1 MeV, and they go down to several tens of micrometers maximum into the surface. We have the solar cosmic rays, which is the next energy range up to about 100 MeV. For protons mostly, these penetrate up to a few centimeters. And then we have the galactic cosmic rays, which are even higher energies, and they don't really have an upper limit, but significant fluxes, they go up to about several 10 giga electron volt. So these first 2 categories here, they're mostly important when we have solar energetic particle events. The quiet time fluxes for those events are very benign, and usually we tend to ignore them. They might be also important when we have magnetotail crossings of the moon. So we know that the moon every now and then crosses, it's not in the solar wind, but it crosses the Earth's magnetotail. While for galactic cosmic rays, these are omnistable, and if you avoid some variations in the scale of, factor of 2 or 3 in the fluxes, mostly of the low energy cosmic rays, then you can consider them as omnipresent and also quasi-stable. Even if you are in the Earth's magnetosphere, this doesn't matter, because these galactic cosmic rays, they can penetrate in the magnetotail without any filling any barrier from the Earth's magnetosphere. Okay, but as I said, I will also talk a bit about the moons of the outer planets, because the Earth moon is the inspiration for the type of science we want to do, the moons of outer planets. There, let's say if we have the same categories, it's just that the sources of energetic particles are different. So we have the suprathermal parts, which are typically generated. You can find them, let's say, in the ring current of a planetary magnetosphere like Jupiter and Saturn, or in the outer portion of the radiation belts. We can have the inner radiation belts, which contain particles from 1 up to several hundred MeV. When we talk about electrons, that's mostly in the 1 to 10 MeV range. When we talk about protons, this can extend up to hundreds of MeV in range. And we have a special category here, which is Jupiter's inner radiation belts, where you can have very high fluxes of hundreds of MeV protons. You might even have 100 MeV electrons. We don't know that, but possible. It's possible. And so it's like cosmic ray energies, but with high fluxes and consistently trapped into a planetary magnetosphere. So the other thing to remember is that when we talk about planetary magnetospheres, these kind of populations here, they are omnipresent, continuously present, highly variable, high fluxes. We have complex ion composition. It's not like the Earth's moon case where we have mostly protons and alphas. We also can have oxygen, sulfur, and so on and so on. And plasmas are of very high temperature. And for the case of Jupiter's inner radiation belts, that's the same. These are omnipresent high fluxes of particles with cosmic ray energies. These are quasi-stable also, extreme fluxes for those energies, and we can also have many different ion species. Okay, so the way that I will organize now the talk is I will, let's say, return back to the solar wind regimes here, and I will start from the lowest energy part and gradually move up to the higher energies and talk to you about what type of science we might do with each different energetic particle regime. So let me start with the first science opportunity, which is sputtering. Sputtering is a process where the precipitating flux of high-energy particles can provide enough energy to the soil so that the soil can release material, mostly neutrals, out of the surface, and these neutrals can contribute one way or another to the moon's exosphere. Now, the moon's exosphere is not really dominated by the sputtering process. It's dominated by sublimation. But during high-energy particle events, solar energetic particle events, where the abundance of very heavy ions like argon, neon, and chromium, you can see here, increases, when you fold this into with a sputtering yield, so that it's more like it's a measure of the efficiency of sputtering. This yield tells you here that, for instance, a 10 keV chromium ion will release 10 particles from the lunar surface, and so on and so on. You can see that these dominate the sputtering yields of helium, which are the ones here. And for this reason, when you have solar energetic particle events, this sputtering component might be dominated actually from these very heavy ion species, even if the fluxes of helium are much higher. So what do we have on this topic? Actually, we do not have measurements. That's one interesting point. Even though the moon is so close, and in principle we can study sputtering, we had the chance to study sputtering for many decades, what we are left over with is simulations. And one of the simulations, you can see it here, is from Killen and co-authors in 2012, where they simulated a CME event. So the CME lasts during this about 50 hours, where you see the gray shaded area, and you see gradually the flux is increasing. And what happens is that you maintain, you can increase the mass of the ambient exosphere of the moon through sputtering up to factors of 20 to 30, depending on the species you assume here that the CME is containing. And when the CME switches off, then of course the exosphere decays, and this kind of time scales of decay, if we are able to measure them, here's a model, of course, but if we are able to match the model with the measurements, then we can also understand the different loss rates of the exosphere. But again, that's a model. And, this is one opinion here. If you look at another paper, it's a review paper by Peter Wurtz in 2007. What he thinks is that this sputtering process from solar energetic heavy ions most likely will have a negligible impact. And the reason he believes this is because he thinks that the sputter yields might change when you have high fluxes. So this is not a quantity that we can define independent of the particle flux. Killen et al. Has this opinion that I described to you here. There is another study by Winslow in 2020. However, he only studied the sodium enhancement at mercury through observation of escaping ions. So we really do not have any consistent pictures. And, this understanding how this works, it's not about which is the dominant process for the exosphere of the moon, but it's understanding the microspecies, the micro processes of sputtering. So it's a very good opportunity to study this. And we can, the way to do it is to remote sense the exosphere during CME events. Maybe that can be done from the Earth, or we can have simultaneous monitoring of neutrals and suprathermal ions in low altitude or even on the surface. There is also, sputtering from Earth's heavy ions that can also give us another opportunity periodically when the moon crosses the magnetotail. So we can use this kind of measurements to understand the microphysics of sputtering and, of course, propagate this kind of knowledge to the outer planet moons. Second topic, which might be interesting with regards to the energetic particles at the moon, is the cases of extreme surface charging. So, as you know, the Earth's moon is an airless body. It's not magnetized if you exclude some minor magnetic anomalies. So the surface of the moon is exposed to UV light and also to solar wind plasma. So the surface, so the UV light will release photoelectrons from the surface. The solar wind plasma will also try to charge the surface negatively because of the high electron temperature, the thermal velocity of the electrons. So these two processes, they tend to fight against each other. So UV, and because the UV, if you release photoelectrons, then you charge the surface positively. The plasma charges the surface negatively, and these two have to balance each other. And when these two balance, then we have a potential, surface potential on the surface, okay, which changes as a function of time and as a function of the solar wind and solar UV activity. And the first very consistent measurements of surface charging were done by the Lunar Prospector orbiter many years ago, more than 2 decades ago. And what was observed, this is a study or several studies by Jasper Halekas in 2007 and 2009, was that you see here that there is a way to measure the surface charging. So if your surface is charged negatively, it emits secondary electrons. And these electrons have a characteristic energy, which is the energy of the surface potential. So, for instance, this means here that the surface was charged up to about 100 electron volts. Here you see that the surface can be charged up to several kilo electron volts, here up to 10 keV. And if you look at what happens in the background fluxes, we see that this is the period when we have the extreme surface charging. We have solar energetic particle events. You can see here, these are solar energetic electrons from the sun up to about 1.8 MeV. These are the proton fluxes, and so on and so on. And this is like the integrated flux. And so when Halekas and co-author, they looked more data, they found out that this kind of extreme charging events, they occur when we have a CME. That's what I described already. But also when we cross the Earth's magnetotail, where we can have energetic particles generated in the plasma sheet of the Earth. So this gray periods is when the Earth is in the magnetotail, and this bar here shows how many events you had per day where the surface charging was above about 500 electron volts. There was observations also from the Chang'e about extreme charging periods also when crossing the magnetosheath. And the studies that Halekas did, he indicates that the relevant parameters which may control the charging is the electron temperature, the energetic proton to electron flux ratio, plus the total electron flux. These correlations, they seem to work. They were partially successful, but not fully successful. So the kind of description of what goes on the surface charging of the moon is currently a bit empirical, and it's not very well explained. So the way to study this is to do a bit more in situ monitoring of what goes on really at the surface. It would be great to have surface measurements or low altitude measurements of surface particle distributions. We might want to do this, at the different regions on the moon, on the wake, at the terminator, where these are regions where the charging can also get extreme values. We might consider also the varying topography, where we have different illumination conditions, and also this can change the charging patterns. And we can also look into another parameter, which is the ion composition, which might also control to some extent. And also understanding the physics of secondary electron emission. This is not so well understood in the literature, so we might need more laboratory measurements that can also help us to understand surface charging. And why this is also relevant, because we can do this kind of science at the outer planet moons. Remember that the outer planet moons, they are continuously exposed to surface charging. So we really need to understand in which way, they are continuously exposed to high energy particles. So we really want to understand the way that high energy particles really contribute to surface charging properties. You can see here measurements by the CAPS instrument on Cassini. That's a moon which is called Hyperion. It's an outer moon of Saturn. And this instrument had different look directions for electrons, 8 different directions. And this, you see here some, at about several 200 to 300 keV, you can see some enhancements in electron flux. And this is actually the direction that the detector was looking along the magnetic field, mapping through the magnetic field onto the surface of the moon. And because the surface of the moon was negatively charged, the moon was emitting particles with electrons with energies of about 200 electron volts, indicating a surface potential of about 0.2 kilovolts on the surface. The same thing we saw at Rhea. This is actually when we flew above the North Pole of Rhea. And you can see that when we are above the North Pole of Rhea, some particles are removed. These are electron measurements by the same instrument. But when we look down, so this is a detector, part of the detector, which was looking really down on the surface. And when we look down on the surface, we normally do not expect to see any particles because they should be absorbed. However, because the moon is charged, negatively charged, it emits secondary electrons. And you can see these beams, secondary electrons, all across the polar crossing of Rhea, also in this detector here. And we also built a model in 2010 trying to explain this, and actually even this gradient that you can see here, that was quite well predicted by our model. However, this model really takes only into account the plasma particles and not the energetic particles, and we really want to understand what is the role of energetic particles in this case. And the moon is, I think, it's a nice test bed to develop our theories for surface charging. Another target in the outer solar system where we can really benefit by studies on the moon is the case of Ganymede, where it's the only magnetized outer planet moon that we know in our solar system. And you can see, because of this magnetization, there is different influx in the polar regions, because here energetic particles from the Jovian magnetosphere can actually access directly the polar regions, but they're less prone to accessing the equatorial regions of Ganymede. So here, most likely, you might have charging dominated by UV, and here you might have charging dominated by particle precipitation. And that's an excellent test case to understand surface charging at the outer planet moons. And we will do this kind of studies with JUICE, but we already want to prepare from now. Okay, another topic where suprathermal particles play a role, and maybe also solar cosmic rays, is the physical and chemical surface alterations. So what I show you here, this is an image at different, mostly infrared wavelengths of the part of the moon's surface which has a local magnetic anomaly. And all these different discolorations that you see here, they have been explained mostly with the precipitation, the diverging precipitation of plasma at different regions. So solar wind is deflected in certain regions, and these regions are the bright ones, where in other places solar wind is focused has a precipitation focus, and you see a much more strong darkening. And where you do not have strong magnetic anomalies, the lunar surface is mostly dark. So these bright regions have been explained as regions where, you know, the lunar surface is less processed by the solar wind. So that was the kind of the standard explanation here. However, when we took spectra, infrared spectra of these regions, what we found out is that the bright regions and also the dark regions here, the very dark regions here, they differ, of course, in the reflectance amplitude, but the shape of the spectrum is similar. So the material looks like it has similarities, and this is not really well understood. So they don't look like they have much different processing. They are both aged in the same way. So a fresh material will look like this with very deep absorption bands, but processed material will look more smooth, like you see here. So it might well be that still what dominates this kind of spectrum, infrared spectrum, is high energy particles, because high energy particles, they are not really dominated, they are not really affected by magnetic anomalies. So we have one case where, so what we might have here is that in some cases, the solar wind precipitation might be masking some effects of energetic particles. But in reality, the spectrum here, the processed spectrum that we see here, might actually reflect some processing of the surface by high energy particles. And we have seen this actually at the surface of outer planet moons. That's a case of Mimas, where you see here a map of Mimas. Mimas is a moon of Saturn. And that's a map of Mimas in the, that's the color here shows the ratio of infrared versus UV reflectance. And this fissile dark region here is due to processing caused by high energy electrons. There are many papers which demonstrate this, that this is the case. The curious thing is that we have precipitation of high energy electrons also on the other side of Mimas, but we do not see this darkening. And the reason is here that on this side, we also have precipitation of dust, and we also have precipitation of plasma. And this kind of precipitation might be masking here the dark region. So you see here that we have the case that we might explain what happens at the moon, but of course this needs more studies and more laboratory simulations, and maybe even some collection of samples from the lunar surface from those regions. Okay, so we move now to another topic, again involving suprathermal particles and also solar cosmic rays. This is kind of a controversial topic. So it's supported mostly by one researcher. His name is Andrew Jordan. So what Andrew Jordan proposes is that we might have processing of the lunar surface up to depths of several centimeters, up to 10 centimeters, let's say, because of the penetration of high energy protons and electrons. When particles hit the surface, some of these protons and electrons, they will penetrate to different depths, which means that if you retain the charge here, you will create from electrons a deeper layer of negative charges, and from protons you might generate a layer at lower depths with positive charges, which means that you can generate between these two layers an electric field. And over time, of course, this electric field will dissipate. However, if the conductivity of the surface is very low, then the dissipation time scales might be slower than the accumulation of the charge here. And of course, if you cross a critical limit, you might collect so much charge, and this electric field here, which it's an electric field developing within an insulator, will be so strong that you might generate a discharge. And these charges can also contribute to the processing of the surface material. The model from another model from Jordan et al. He developed his model taking into account what happens when you have strong solar energetic particle events, which can deliver over short time very high fluxes of particles. And he generally found that we do not really have the chance to generate discharge events, except maybe at the lunar poles, where because of the low surface, the low temperature that you have in craters, the conductivity is even lower, and therefore the accumulation of charge there can be even stronger. So the probability to have discharge events in the lunar soil is higher, where you see here the red color, and mostly prominent in the polar regions. So we do not really have much data about this, or whatever data we have is really indirect, very, very indirect indications of about internal charging and electrostatic discharges taking place. So according to Jordan and co-authors, so the evidence which is favoring dielectric breakdown is observation of increased soil porosity. According to them, discharges might cause this. Some more confined in particle distributions means that we have narrow particle size distributions at the polar regions, and also some latitudinal reflectance variations. So he built an empirical model here where we see the reflectance from the moon at this wavelength here increases sharply towards the pole, whereas from other models which do not consider electrostatic discharge, this amplitude increase would be much smoother. The evidence against dielectric breakdown is that the high near-infrared albedo in PSRs, PSRs means permanently shadowed regions on the moon, which according to Jordan also this might be a conflicting evidence. Also, there is a theoretical paper by Hapke who suggests that the secondary electron emission driven by internal charging might reduce subsurface electric fields, and therefore discharges will not occur. So we really have to think, energetic particles are involved here, and we really have to think what are the direct dielectric breakdown discharge observables. Maybe we need to have surface measurements of energetic electron and ion fluxes in the polar regions, try to constrain also secondary electron emission. Maybe we can look for remote sensing and check for emissions in UV, visible, or radio wavelengths, which might indicate disruptive events on the surface, and also possibly current measurements in the soil, but that's really not my field, but it's something to consider. Why this topic might be interesting because, remember, we have a very extreme high-energy particle environment in our solar system. That's Jupiter's inner radiation belts. And within those radiation belts, we have some small moons. You know, for Jupiter, we know mostly the Galilean moons, but we have also some extra moons very close to Jupiter, like this moon here, which is Amalthea. And this moon is really the most heavily irradiated object, most likely, in our solar system. You see the fluxes here are up to the 10 to the 7 per square centimeter per second of greater than 10 MeV protons and over 10 to the 8 MeV electrons continuously. Whereas for a strong SCP event, you know, the fluxes here are 3 to 4 orders of magnitude lower, and these do not last more than 1 day. So conditions for electrostatic discharges, you can see they're very bad here. At 5 Jovian radii from Jupiter, actually this moon orbits at 2.5 Jovian radii from Jupiter. So you can imagine how extreme environment it orbits within, and maybe discharges from this moon might be very important. Another topic is, you know, if this comes from laboratory measurements and again involves suprathermal and solar cosmic rays, is understanding what we call these features. If we zoom into samples of the moon, we see this region here, which is called a rim. And these rims are considered to be formed by solar wind precipitation. Understanding how these rims form can also give us insights about the history of precipitation from solar wind and high-energy particles on the lunar surface. The reason why this is interesting in the context of energetic particle science is because it's still very unclear which particle species and energies contribute to the development of those rims. And until very recently, it was always thought that the solar wind is what controls the development of these rims. However, there was a recent study by Andrew Poppy and co-authors where he also found that like the suprathermal component of the high energy particle solar wind electrons and ions might also contribute this. So that's another topic to study here, and the way to study this is to do a direct correlation of samples with detailed measurements of the in situ precipitation environment at different regions of the moon. So let's say if we want to isolate the solar wind from energetic particles, we can go to lunar magnetic, from solar energetic particle effects, we can go to lunar magnetic anomaly regions, or we can go to regions with different topography where different particle components are shielded with different efficiencies. So then we can separate, you know, the contributions from plasma and solar energetic particles. Okay, now we move a bit higher in energy. This kind of topic involves both solar and galactic cosmic rays. And this concerns about the lunar albedo particles and also albedo photons. So what happens here is that, you know, when we have solar energetic particles or galactic cosmic rays, this can penetrate quite deep into the surface, but also they can impart a lot of energy into the soil so that you can release particles from the soil and photons from the soil, which might be indicative of what is going on in the low subsurface of the moon. And the first direct observations of these albedo protons was done by the Lunar Reconnaissance Orbiter, and you can see them here. So this is a spectrogram where it shows the deposition of energy in different detectors of this instrument, which measures energetic particles. So this instrument is looking upwards and downwards. So these are the protons from the upward detector that you can see here. And the downward detector, which looks onto the moon surface, is this one here. And you can see this is the corresponding high energy protons coming from cosmic rays and solar energetic particles. And this is the reflected protons, which is coming from the surface. And we had a lot of simulations where they predict here, you see all kinds of different albedo species. So what we have measured so far is mostly albedo protons. We have predictions from albedo alpha particles, heavy ions, and electrons. These have not been measured, but let's see if they are actually interesting to measure. But before doing that, remember also that the precipitation of high-energy protons, cosmic rays mostly, can also lead to the generation of gamma rays, and this is how we can do gamma ray and also neutron spectroscopy. And we can also generate maps of different lunar composition here. But when it comes to lunar albedo particles and photons, there have been several simulation studies where, according to those studies, some of them, they say here from Zaman et al. That that the proton spectrum, unless you go to very low energies, like between 1 and 10 MeV, where you might see some differences according to the soil composition, with high precision, you need a very high precision measurement to resolve those. You might not see any differences, in the spectrum. You might see mostly differences in the neutrons, in the gamma rays. So, according maybe to Zaman et al., it might not be worth measuring albedo protons or electrons. He has the same conclusion for electrons. However, if you go to another study by Squadron et al. In 2015, he finds, with measurements from the Lunar Reconnaissance Orbiter, that the albedo protons, they have a gradient as we go from low latitudes to high latitudes. And remember, at high latitudes, actually, this is the place where we might have subsurface ice. And when you have subsurface ice, you expect that this will block albedo protons. So if there are protons coming out from the surface, they are much more efficiently absorbed by ice if it's present there. So actually, we would have expected the reverse gradient. So the proton flux is decreasing with increasing latitude. But we see the opposite. And the way that Squadron explains this is that if you assume that the water ice is actually distributed in a certain way, in certain layers in the subsurface, then actually, in this case, you might get this kind of dependence that is visible here. So again, these are two conflicting studies about the role and the type of measurements we can do with energetic particles, which means if we have conflicts, we have to resolve them. So we need more measurements in that respect, possibly low altitude measurements or even surface measurements, and high precision. High precision is very important here because we have to resolve, as you see here, very small difference in particle fluxes. So we need these albedo particle measurements with very high precision and possibly closer to the surface. Maybe this type of science is something that we can do even with JUICE. We have some instruments on the JUICE spacecraft. This is the GENI energetic neutral atom and also energetic ion detector. Typically, this works at energies at below about 2 to 5 MeV, where the albedo particles are not so high in flux, but it's a very big instrument here, and it has a very high sensitivity. It will continuously look down to the surface of Ganymede, and maybe we have the chance to get a lower energy component of albedo protons or even heavy ions at the case of Ganymede. But this has to be studied also at first, theoretically. Another topic, let me see how much time I have. Well, not much time, so I might have to skip some slides, but this also involves solar and galactic cosmic rays and concerns the production or the generation of cosmogenic nuclides. So, when you have precipitation of very high energy protons into the lunar soil, this will create some neutrons. A lot of these neutrons escape, and this is how we can do neutron spectroscopy of the surface, but also you have a lot of neutrons will go into the soil, and they will interact with the material there, and they will contribute to the formation of what we call the isotopes here, these cosmogenic nuclides, which over time they accumulate, and actually by measuring those at different depths, we can provide some dating information about the lunar soil. And you can see here a very nice simulation. So when we take samples from the moon and we measure as a function of depth the production of cosmogenic nuclides, you can see a very nice model correlation with the measurements, with the low depth component here mostly coming from solar energetic particles and the high depth component coming mostly from galactic cosmic rays. But that's one of the good plots from this paper. If you look at this paper, you will see that there are cases where we have deviations. And of course, the deviations are always the interesting ones, because especially deviations at low depths will tell us something about the irradiation history from solar energetic particles and respecting weathering effects. So deviations might be caused by weathering effects like a crater, like meteorite impacts and formation of craters, or changes overall on the lunar surface over time, and even changes in the solar energetic particle component as a function of geological timescales. So you can see here this kind of measurements have been used to calculate. This is kind of a space weather study here, to calculate how frequently you get extreme solar energetic particle events in the history of the solar system. That's what we can get from satellite observations, in situ observations of the solar wind. If we want to track extreme events in the history of our solar system from the sun, we have to use lunar samples, because they maintain within their soil, within this soil, we can find evidence of what has been going on over really the history of the solar system and the activity of the sun here. Can we do the same thing at the outer planet moons? It's a bit something to dream of, but yeah, there are some studies in the literature where we can discussions about how we can use lithium, beryllium, and boron, or other noble gases to do in situ studies and geochronology studies with landers. We actually had the first ever geochronology experiments on the MSL Mars rover. You can look at the study by Cohen and co-authors. And that's something maybe too futuristic, but something to consider for the young generation. Since the next L-class planetary mission from ESA is now, we now know that we will target to put a lander on Enceladus. The experiments are not yet defined, and we might think whether we want to do these geochronology experiments on the surface of the outer planet moon. Okay, I skip one slide here. I just want to talk about maybe the most futuristic project that we can do with energetic particles at the surface of the moon. This is called muonography. This really depends on the irradiation of the surface by galactic cosmic rays. As you know, here on the surface of the Earth, we do not really get directly cosmic rays. What we get is muons, because cosmic rays, they interact with the atmosphere. Muons are secondary particles as a result of these interactions. And the muons are very transmissive into material, and we can actually use them to penetrate very deep into the soil of the Earth. And using muonography, we can study, the interiors of volcanoes. We have recently discovered that, there are hidden chambers within the Great Pyramid through this muonography. Of course, at the moon, we don't have pyramids, we have mountains, but we have all kinds of geological structures. And it's close, so we can send very big experiments, maybe not in the next decade, maybe in the next 2 or 3 decades, but it's something possible. And some studies have already started appearing about the feasibility of doing muon measurements. So what you do is usually you put different muon detectors around the target, and you correlate measurements of secondary muons at different locations. And by inversion techniques, you can image the interior up to several meters or even up to several kilometers, depending on your sensitivity. Okay, so yeah, that's the final slide of my talk. I just wanted to demonstrate to you that, energetic particles are not just about space weather at the moon. You can do many different things. If you think about our 3 different regimes here, suprathermal, solar, cosmic rays, and galactic cosmic rays, I have mapped the different topics that I have talked about here into the different categories. You see many different topics that we can really study with, that we really need understanding of the high energy particle environment of the moon to make progress in any of these different science topics. And also some more topics that I don't have time to talk here about: cosmic ray transport, Muonography actually talked about. Also, the cosmic ray-induced ice chemistry might be another topic. What I also want to stress here is that when it comes to measurements and instrumentation, for measurements in this regime, we do have the instrumentation. We have capable instrumentation to do what we need. So what will really help us make any progress is actually what type of mission profiles we choose and what is our measurement strategy. When we rely on secondary particle measurements from galactic cosmic rays, here what is very important, and we are not capable of doing this yet, is to have very high precision spectroscopy measurements of high energy cosmic ray particles, which is not yet possible, at least with the instrumentation that we have for a moon mission. On top of this, what also is important is that, of course, contextual measurements are important. We might benefit from remote sensing of the lunar exosphere from the Earth if we want to understand, sputtering, for instance. And of course, comparative planetology is also very important in that respect. And with that, yeah, I finished my talk, and I'm happy to get any questions you may have.
Yeah, thank you so much, Elias. Yeah, I think that you collect a great number of very interesting information. I think you spend a lot of time in doing that. And any questions from the audience? It's usually not a common topic in lunar science, using energetic charge particle.
Yeah, it took a lot of time to find all these topics.
Yeah. On the other hand, there are some very interesting applications. The one slide you have that about the energetic charge particle, namely electrons charging one layer, and then charging another layer with positive charge, right, like that. Who did that study?
His name is Andrew Jordan. I think he's one of the few, or maybe even the only advocate of this topic.
Yeah, I know, but it's very, very. We heard about.
Very interesting. It's very interesting topic. It's very difficult with the type of measurements we have to really validate it, or even find any good, let's say, measurable for validating this topic. But well, we know discharges happen. It's a matter of parameters in the end.
It's Jordan, right? Jordan. I see that 2014, 2015. Yeah.
And there are many more papers about this topic.
Oh, okay.
But yeah, a lot of parameters have to be assumed, and I think it's a model which is really sensitive to the input parameters. A lot of simplifications which are done, and as I said here, there are some people like Hapje here who does not really believe those results. But I think it's kind of controversial. It's just that currently it's mostly supported by one author, so it's difficult to make progress in this case.
Anyone has questions? If you have questions, just ask.
Hi, Elias. I'm Betty.
Hi, Betty.
Hi. So I have a question about Amalthea.
Okay.
You said that Amalthea received almost the highest flux, many like high flux of charged particles. I'm just curious about, do they found anything interesting of Amalthea's surface after receives so many charged particles?
I know that, Amalthea is a very difficult moon to study, first because it's very small. I think it's about 100 kilometers or a bit less across. You see here it's an irregular moon, and it really orbits within the most extreme environment of Jupiter's inner radiation belt. So typically spacecraft do not go there. So we have mostly spectra of the surface using remote sensing from the Earth. They do demonstrate that this is a highly processed surface. I think it's they always talk about a very reddish kind of type of spectrum, which is kind of unexpected for a moon of this location. There are some other moons of Jupiter where, of course, they compare to with, and they do not see any similarities in the spectra. And possibly processing might have to do of the surface might have to do with the presence of high energy particles. Complication there is that Amalthea, and there are also some other moons which are called Metis and Adrastea. And Metis and Adrastea are a bit further inside, also very highly exposed to radiation. The complication with those moons is that they are also interact continuously with the faint ring of Jupiter. So it's a bit unclear to what extent, the ring interaction or the energetic particle interaction contributes to the visible spectrum of those moons, the spectrum that we can get from the Earth. But of course, there should be some heavy processing from energetic particles, whether it's on maybe at a deeper layer or at the top layer. That's a bit still to be determined, but it's a very difficult measurement to do, as I said.
Okay, I see. Thank you.
The JUICE spacecraft might have some opportunities to get spectra of those moons, and so the JUICE, they're planning a campaign for ring observations and also measurements or spectral measurements for Amalthea, Metis, and Adrastea. And I think one more is also Phoebe, which it's slightly further out. So this is at 2.5 and Phoebe is at 3.2. Jovi and Rendier.
Okay, thank you.
The ions you're talking about, for Jupiter, there would be heavy ions like oxygen and sulfide. And would that make a difference from using the protons?
Yeah, I mean, the role of heavy ions is a bit, let's say, controversial because the heavier, the more massive the ion is, then the faster it loses energy as it penetrates in the soil. So heavy ions, they can really irradiate they might affect really the first top millimeter of the surface. Even if you go up to energies of hundreds of MeV per nucleon, you do not penetrate more than a few millimeters. And so when we study the Earth's moon, for instance, they can more easily identify effects of irradiation by protons and maybe solar energetic alphas, but they do not see much evidence for irradiation by heavy ions, except maybe in few cases. And one of the reasons is because heavy ions affect the first top few millimeters, then there is processing of these few millimeters by other processes like solar wind. They might be processed by micrometeorites. So it's easy, let's say, to destroy the effects of heavy ions.
Alice has raised his hand. Okay, Alice, you have questions?
Yeah, I have. Yeah, sorry.
Please.
Yeah, microphone. Do you hear me? Fine.
Yeah.
I'm interested about radiation background, radioactivity of the moon surface. Do you have any estimation or measurements of this feature, important feature, which is actually important for human and for water, which we get from the moon? It will be radiative, yeah? It will contain radiation. Did you make any measurements?
So do you mean the albedo particles?
It's not albedo. It's some radionuclides, some radioactive nuclei, unstable nuclei in the soul.
The natural radiation from...
Yes. It's not natural. It is actually activated or generated radiation by galactic cosmic rays, yes, by solar energetic particles.
Yeah, so we do have a lot of measurements. You can see here, it's not the only maps that we have. These are mostly the first maps, detailed maps that we have of generated radiation from the lunar surface. We have three types of radiation. One is the gamma rays, and we use this to. This has been used mostly for probing the subsurface composition. The same thing has been done with thermal and epithermal neutrons. Several orbiters have done this. These are all the measurements by lunar prospector. This is mostly for the composition of heavy elements. This is mostly for the composition of water on the lunar poles. Currently, we do have one of the lunar rovers, one of the Chang'e, I think Chang'e 4, which has an energetic particle detector from the University of Kiel. And this detector is also able to measure neutrons at higher energy. And I think within orders of magnitude, when we do about studies about radiation protection, the precision does not have to be so extreme, but the approximate fluxes are similar to what the models really would predict for neutrons, gamma rays, and also for albedo protons. So currently, yeah, we do have measurements. They accumulate over time. What we are really missing is the capability to make measurements of albedo radiation with very high energy resolution and also with very high precision in the flux determination and also the energy determination. So what you will see from measurements, for instance, for albedo protons. So albedo protons, let's see here, it's this blue line here, if you follow my cursor. Typically, you have one measurement here at about 100 MeV and another measurement at about 10 MeV. So we don't really have a good resolution of all this spectrum here. There are instruments which have been proposed where they can do this kind of measurements. If you are, let's say, familiar with the Pamela experiment,
Yes.
in Earth orbit, it's not functional anymore, but there is correspondingly the AMS. So there is progress in kind of miniaturizing this kind of instruments, doing magnetic spectroscopy with very highly pixelated detectors and trying to get spectra with very high fidelity and very high precision. These instruments have been proposed. They have not flown yet. They're being tested. Prototypes are being built, but that's something we are missing.
Thank you very much. Thank you.
Okay.
Okay. Chinese, is it Chinese Sana? You have questions?
Hello, can you hear me?
Yes, I
Yes.
can hear you.
Yes.
Yes, I have a question regarding the slides where you talked about the extreme surface charging. And you said that if the electron temperature is like 200 electron volt, it will acquire a very high potential. So, do you think that the surface electric field will be of the order of similar?
Sorry, there is some background noise. It sounds like wind. But I kind of missed your question. Can you repeat it again? It's about surface charging, yes. But what was
Yes, for a high electron temperature, you said that the electric potential on the surface will be very high. So, do you think that the electric field will be of the order of similar kind?
Yeah, I mean, electron temperature, that's mostly a plasma parameter here. That's why I did not highlight it, because the focus of this talk was high energy particles. But yeah, the electron temperature practically determines the thermal velocity of the electrons. And
Yes.
this will determine, let's say, the level of negative charging that you might have on the surface. So this is what is fighting the positive charging that you get from the UV irradiation from the sun. Yeah, so correspondingly, yes, when the surface potential is due to electron temperature is the negative potential is high, correspondingly also the electric field will be high. Of course, the electric field of a charged surface will decay very fast. It decays over length scales of a debye length, several debye lengths. And it really depends also on other parameters of what the length of the debye length will be. And, you know, for how high above the surface you might have this strong electric field. These electric fields have been responsible for for some people for levitating dust and even levitating dust to very high altitudes, even though these models now are a bit more, let's say, conservative compared to what they were in the past. So these electric fields might be responsible for transport of dust, charged dust on the surface, but not really for the possible injection of charged dust to very high altitudes. But yeah, you might develop very strong electric fields, yeah, just because of electron density.
Because if you see the Debye length, it is inversely proportional to the square root of density, electron density. So if the in this location the density is quite low, so the Debye length would be of the order of a few hundreds of meters to kilometers. So if you have a very large potential and if you divided it by large Debye shield, the electric field might not
Yeah,
be that.
you can have that. That's where, let's say, when you start moving away from the assumption of the very purely spherical moon, and you start to introduce topography, you might go in a crater, for instance, and within a crater, because of the topography, you might block the low energy component of the solar wind, so the one that contributes to the density mostly. But you might have the thermal electrons, which determine
Yes.
the temperature. They might be more mobile and they might penetrate into the crater. And there you can have a very high temperature plasma and simultaneously a very low density plasma. And then your Debye length can be very large. That's why when we look at about strong electric fields, we look at terminator regions where, let's say, topography and lunar and topographic shielding of UV radiation and also the precipitating plasma can play a much more important role compared to when you are, let's say, in the subsolar region on the lunar surface. And there you can, yes, you can create at the terminator, for instance, very strong electric fields. The same thing you can also generate in the lunar wake, where we do not have UV to cause, positive charging. And you might have the first things, the first particles which enter into the lunar wake are high energy electrons, the most mobile ones. So there you can also have cases of very extreme charging, which can also contribute to processes like charge mobility, strong electric fields, and so on and so on.
Okay.
Yeah, it's kind of debatable, still. From the measurements, we have not seen negative potentials more than, I would say, 5 kilovolts on the lunar surface.
Now, if you have still questions, I suggest you write to Elias. I mean that you must have you have a lot to chat to ask him. I think that time is up. And then we would finish the session just right now, and want to thank Elias. And then, as I said, if you have questions, or comments, you could write to Elias, and I'm sure he will be happy to respond. You could find his email address very easily. Just look at the paper written by him. There are plenty of them. It's Roussos at MPS, right? Or
at mps.mpg.de.
Yeah, but if you
I'm also happy to share the presentation.
Right. If you actually, yes, I mean that if you want to have a copy of Elias' slide, I mean he said he was going to send to me, so just write to me. Okay, good, and thank you, and good morning again. Have a nice day, Elias.
Have a nice afternoon. Thank you again for the invitation, and it was very nice seeing you all.
Right. I hope to see you again soon. Yes.
Okay, great.
Bye-bye.
Bye.